Okay, so this is business calculus, and so the next example is of fundamental importance for this course. We're going to talk about optimizing the cost, the revenue, and the profit for a company. So the example is a little bit artificial, so we're going to imagine a company that is producing units of something, and we're not even going to say what those units are, but the number of units that this company is producing is the variable X will represent that, the number of units that the company is producing. And the next thing that you need is the cost function. So the cost to produce this many units, that's what C of X represents. And in this example, the cost to produce X units is 4 times X plus 10. So if you produce 5 units, the cost to produce 5 units is 4 times 5, which is 20, plus 10 is 50. Okay? And the other fundamental quantity that we need is the revenue. That's how much money is generated when you produce X units, when you sell them. And the revenue in this example is 50X minus 0.5 times X squared. So in these problems, you'll be given the cost function and the revenue function, and your objective is to find the number of units, the value of X, that maximizes the profit. So to do that, you got to know what the profit is as a function of the number of units, and that's the revenue generated, the amount of money you make, minus the costs to produce all of those units. And in this case, I have a formula for the revenue, and I have a formula for the cost, and so I just need to write those out. I guess it's useful to point out that I managed to remember the parentheses around 4x plus 10 because I have to subtract the entire cost function. Okay, simplifying is always a good thing to do at this stage. So I've written negative 0.5x squared first, plus 46x. That comes from combining the 50x and the negative 4x right here, minus 10. So that's the profit function. And now the task is to maximize this function, and that we know how to do. I should take the derivative, set the derivative equal to 0. So it's negative 0.5 times 2x plus 46. If I simplify that, I get negative x plus 46 because the product of 0.5 and 2 is just equal to 1. And if I want to find the critical points, I should set this derivative equal to 0, and that means negative x plus 46 is equal to 0, and I can solve that, right? X must equal 46. So that's the critical value, and the second derivative of this profit function is clearly negative because it's just negative 1, which tells us that this is an absolute maximum. So the maximum profit is at at the value x equals 46. So that's attained when x is 46. And to find the actual maximum profit, I have to plug 46 into the formula for P. So that's this formula right here. And also you can check this. You plug in 46 and you wind up getting the value 1048. Okay? And that's the way to find the maximum profit for this particular example. All right, so the next example is how to maximize revenue from ticket sales. So the situation is you have a football stadium and it's charging $30 per ticket, and averages about 20,000 people attending every game. Each person spends about $8 in concessions. So let me write that out. Okay, so the stadium management has figured out that if they lower the ticket price, attendance will go up, and they've really quantified this by studying previous years. And here's what they've learned. For every drop of $1 in ticket price, the attendance goes up by about 800 people. Okay, so then the problem is to choose a ticket price, maybe it's not $30, maybe it's more, maybe it's less, that maximizes the revenue generated. And revenue is going to include ticket price and concessions, okay? Okay, so to make sense of this, it's a good idea to draw a graph or two. So in this graph that I'm drawing now, the vertical axis is the number of people in attendance, and I chose three values: 20,000, which is what the stadium typically charges, and then 20,800 and 19,200. And the horizontal axis is the ticket price, and I've chosen just three values: $30 per ticket, and $29 per ticket, and $31 per ticket. So here's what we know, that when the ticket price is $30, the number of people that are in attendance is 20,000. If you increase the ticket price by $1, the attendance goes down by 800 people. That's why I chose 19,200. And if you decrease the ticket price by $1, the number of attendees goes up to 20,800, and that's this dot right there. So there's a straight line that we're staring at, and that's about as straight as I can draw it. So one of the things that we need to do in this problem is to find the equation of this line. So find the equation relating the number of people to the ticket price. Now, well, we know the slope, because if you either increase the ticket price by $1, you know that the number of attendees goes down by 800. And if you decrease the ticket price by $1, the number of attendees goes up by 800. And so the slope should be negative 800. So the slope of this line is negative 800. So now I call upon all of us to remember the point-slope form of the equation of a line. So here it is: y minus y1 equals m times x minus x1, and the line passes through the point x1 comma y1. And in this case, that is 30 comma 20,000. So summarizing, in this graph, the number of people is y, the price is the x coordinate, and our equation becomes y minus 20,000 is equal to negative 800 times x minus 30. And that can be simplified by first multiplying out the right-hand side and then moving the 20,000 over to get y equals negative 800x plus 44,000. And in order to find a formula for the revenue as a function of the ticket price, we had to first find a formula for the number of people that are attending as a function of the ticket price. And that was an involved process that I did on this first page. And with that formula, then I could... Okay, so summarizing, we have chosen to let the variable x represent the ticket price, and we found a formula for the number of attendees as a function of ticket price. So the next thing we need to do is find a formula for the revenue generated as a function of the ticket price the stadium might choose. That's going to be the function r of x. And the formula is, well, the number of people who attend times the amount spent. The number of people who attend is negative 800x plus 44,000, and each person spends the ticket price plus $8 in concessions on average, so I can write times x plus 8. Now this can be multiplied out to get a quadratic function, and I'm going to write out the answer, and you guys should double check that I've done my work correctly. Okay, so verify that if you FOIL this out, you do indeed get this formula here. And in order to maximize the revenue, I now have a standard procedure. Look for critical points. In this case, there should be only one because it's a quadratic function. Because this is a negative sign in front of the quadratic term, I know it's going to be concave down. And so the critical point that I find is going to be a max. So let's do it. The derivative is negative 1600x plus 37,600. And I need to set that equal to 0, which I can simplify. And dividing by 1,600, I find the answer, $23.50. So the maximum revenue is achieved by setting the ticket price at $23.50. And if you want to know how much money is generated, you take that number, $23.50, and put it back into the revenue function, which is $793,800. Okay, so summarizing, for this problem, we weren't given a formula for the revenue. We were given all the information that we needed to determine a formula for the revenue, but there was a little bit of extra work, and the starting point really was this idea that the revenue is going to be given by the number of people who attend times the amount they spend, and both of those quantities depend upon the ticket price. So we had to go back and figure out a formula, which is this formula here, for the number of people who are attending as a function of the ticket price X, and that then we could plug into the formula for the revenue. So in such problems as this one, you may have to sit and think a bit, what formula do I need to represent the revenue? And in order to do that, I probably have to find some auxiliary functions. So you got to keep your wits about you. And some of these problems in business calculus, as well as in the business world, they take a lot of thinking before you can write down the appropriate revenue function. That's part of what makes the business calculus exciting. Okay, good luck.